In the previous video, we learned about the functoriality of functions and how it allows us to construct functions out of higher inductive types. But first, there is something we should note about functoriality. Recall that the functoriality of functions implies that functions map not only the points out of a type, they also map the paths out of a type. In other words, functions are continuous. But what about dependent functions? Suppose we had a type A inhabited by the terms x and y, and we had a path P from x to y. And suppose there were a type family capital P, such that we can speak of a dependent function mapping any term x in A to the fiber Px lying above it. Let's assume we have such a function, f. One would assume that for f to be continuous, it should be possible to construct a path from fx to fy. But since fx and fy aren't of the same type, we cannot do so. However, we can construct a path in the total space from x fx to y p star of fx. Then, to complete the path, we can use the path induction principle to construct the path APDF of P in the fiber lying over y from P star fx to fy. Let's take a look at an example. Suppose we wanted to construct a dependent function out of the circle type. And let us again call the type family P. To construct our dependent function, we only need a term B in P base, and we need a path L from loop star B to B. In that case, there exists a dependent function f such that f of base is B and APDF of loop is homotopic to L. It now becomes clear that whenever we construct a dependent function out of a higher inductive type, we are describing a section of the total space that looks like the base space. That's why topologists call this a section. We now know how to construct sections in homotopy type theory. Thanks for watching.